I wanted to apply machine learning to something practical myself. I chose to apply it to NumerAI. It's a hedge fund where trades are determined based on predictions crowdsourced from data scientists, given anonymized data.
First, a flashback to 2017.
The weekly dataset downloaded from NumerAI website contains two data files. NumerAI Training Data CSV, which contains records including ID, era, a set of features, and the target value. NumerAI Tournament Data CSV contains the same fields except for the target, which is supposed to be predicted by the data scientist. Examples of a simple training and prediction code implemented in Python language. The Pandas Python module is used to load the training and tournament data. A list of feature column names is used to extract the feature values from training and tournament data. The target column is extracted from training data and the record ID column is extracted from the tournament data. After the training and prediction is done, the record ID from the tournament data is joined with the results of the prediction, and the joint data frame is written to prediction CSV file. Scikit-learn module is used. An untrained model is created. In this example, it is linear regression. Then, the model is trained using feature and target values extracted from the training data. A prediction is made on the tournament feature values and only probability that the target is 1 is used. It is returned in column 1 by the prediction. Looking for inspiration, I came across the Tech in Pink blog where the author is giving a couple of examples. Searching further, I also found an interesting post on FastML blog where the author applies random forest and logistic regression learning methods with data transformers. Beside Googling for blog posts about NumerAI, I also searched GitHub directly. That's how I found this repository published by the user Jeremy123W, which applies gradient boosting and deep neural network learning methods. In my search for inspiration, I came across a post of Jim Fleming on Medium. The code also raised a few deprecation warnings. In particular, the cross-validation and grid search were moved to the model selection module. There was also some obsolete Python 2 code which needed to be updated to Python 3. I also updated the calls to the deprecated TensorFlow and scikit-learn functions. As it turns out, the submission process may fail if the probability is equal to 0 or 1. Therefore, it was necessary to find out the granularity of the floating point type and clip the probabilities to an open interval form 0 to 1. One of the observations I made was that earlier the features had uniform distributions. But currently the distributions were Gaussian. Since among the models there are ones using neural networks, I decided to normalize the features using standard scalar instead of min-max scalar, though I realize that choice may be misguided. For some of the learning methods it is possible to use all CPU cores, and in scikit-learn this can be enabled by setting n jobs to -1. The code uses multiple models, random forest, and support vector machine, gradient boosting and deep neural network learning methods. One decision to make was which learning method to use. Another decision was which values of the hyperparameters to use, and I used grid search to automate it. Yet another decision was related to the application of feature engineering, which could be feature scaling or normalization, or calculating polynomials of the input features, or application of other functions. But what if all that could be automated? Turns out there are frameworks which do just that. One such framework is Python-based Autosclearn. There are more frameworks automating application of machine learning. AutoWeka is another example, this time, Java-based. In another example, Teapot. This is an automated machine learning framework, using genetic algorithms. The input data for the models is prepared by applying a method called adversarial validation. There are also additional features added to the input data by applying a dimensionality reduction method called TSNE. But I replaced it with an implementation making use of multicore processing for two-dimensional TSNE. We want to combine those predictions somehow though to improve the results. To combine the predictions we will go through the sorted list of reports and combine the best two which were not tried yet. You may have noticed that the method combining the predictions is called ensemble. Over time you will observe the ranking file being populated with various ensembles of the predictions from the base models. This simple method allowed me to reach very good results. To keep the code clean, I decided to wrap the code in a Docker container. To make sure the container is rebuilt whenever I make a modification, I use the Travis CI. I chose to organize the pipeline of the computational tasks with Luigi. The tasks will be running as Docker containers, and to kick off the computation the data will be downloaded using the NumerAI API.
Now let's fast forward to 2025.
Lightweight compartmentalized Docker images are great for production where you want to keep dependencies down to minimum and startup time short. However, this is a hassle for experimentation. Therefore, I packaged everything in a single Docker container image. I dropped Luigi and switched to good old scikit-learn, pipelines, and by the way, I switched also to GitHub Actions instead of Travis CI for my automation. I also started to use weights and biases where I store my trained models as artifacts and model pipeline configuration. I store there also plots and tables, which visualize hyperparameter search cross-validation results and model ranking, and I use it also for training, monitoring, and logs. For even more flexibility, I am using Hydra configuration files for the definition of model architecture, and as mentioned earlier, the configuration file is saved to weights and biases together. This allows me to decouple software dependencies from the model architecture and execute A/B testing. If there is one flaw of my previous approach, it would have been not taking into account the overlap of the eras when applying cross-validation. So I corrected the oversight by implementing a specialized cross-validation splitter. Given the change to the data, I now use regressor models instead of classifiers, and given that I now lean more on scikit-learn, I also expanded the list of scoring functions.
With the switch to features quantized into 5 distinct values, I decided to drop using scaling, which by the way allowed me to switch to 16-bit precision, and because the number of features grew and their correlation is now very low, I also stopped generating polynomial features.
In the meantime, AutoWiki and AutoSclearn fell into disrepair and are no longer maintained, so I got rid of them and decided to have a cleaner code. I made it fully typed, and at the same time, I started using linters and type checkers. Finally, rather than relying only on CPUs, I switched to CUDA where possible, and I also ported TensorFlow code to PyTorch-backed Keras and switched to using OpenCL for LightGBM.
Thank you for watching.